Welcome, everyone. For today's prep, I want to look at one more exponential growth example. So we're back to looking at our colony of fruit flies here. And we know that this colony is exhibiting exponential growth. So we want to keep that in mind. And we also know the initial size of the colony here is 100. So there's 100 fruit flies to start with. And then it doubles in size in 9 days. So from this information, we want to figure out what the growth constant K is. All right, so let's kind of unravel all the different information we have. So first of all, we see that wording exponential growth. So that's telling us essentially what the population formula should be. So our population formula, we'll call it P of T, should be P0 e raised to the KT. And if we remember, P0 is our starting population and K is the growth constant. So we need to figure out both of these values in order to have our population formula all figured out. All right, so let's start with our initial population. And we're actually told what this is. So we're told that the initial size of the colony is 100. So this right there is telling us that P0 is 100. All right, so as soon as we know that, let's update. So we can get a nice little update here to our function. Let's fill that in. So our starting population is going to be 100, so we can fill that in. And then we just have that exponential term, e raised to the KT. All right, so what do we know? What else do we know? Well, we know that this population doubles in 9 days. So what does this tell us? Well, it tells us that the population after 9 days should be double our starting population. And since we know our starting population, we can actually fill that in. Now it turns out this is enough information. We don't even need to know the starting population in order to figure out the K value. But since we do, we might as well fill it in. And our population, if we're going to double in size after 9 days, if we're starting with 100 fruit flies, well, double that would be 200. So we know that after 9 days, we should have a population of 200. So this info right here is going to give us essentially an equation that we can use to solve for K. So let's see how this works. So we're going to take that info. P of 9 should be equal to 200. And the idea here is we're going to plug 9 into the equation that we have so far for T. And the output should be 200. So let's see what we get when we do that. So we're going to evaluate at T equals 9. So we'll have our 100, then we'll have e raised to the k, and we're plugging in 9 for t. So we've evaluated in our function here, wherever we had a t, we plugged in 9. And we know, based on that information, that this should be equal to, nope, not 400, 200. So we know the output of this population function should be 200. So we set this equal to 200. And what this does is this gives us an equation, an exponential equation, that we can then use to solve for K. And so we've been practicing how to solve these exponential equations. So now we just have to isolate the exponential term. So we want to get that exponential term all by itself. So the first step would be divide both sides by 100. So we end up with e to the 9k is equal to 200 over 100. And we could simplify that down. And then once we get the exponential term all by itself, we want to get rid of the e, so we're going to apply natural log to both sides. So we get natural log of e raised to the 9k is equal to the natural log of 2. So I'll simplify that 200 divided by 100. And the natural log nicely cancels out our exponential. And so when we keep solving, we end up with 9k is equal to the natural log of 2. And then finally, k is equal to the natural log of 2 divided by 9. And so that's our exponential growth constant. All right. So the whole point of being able to get this population function is to kind of make predictions about where the population is going. So for part 2 of this, we want to be able to answer how large the colony will be after 41 days. So all this is really asking for, we want to know essentially what is the size of the population when t is equal to 41. So to answer this, we're just going to plug 41 into our population function. So what's our population function? Well, we did find that it was 100 e to the kt, and let's do a final update there. So we know what our k value is, so we can do one more update to that function. So the population is 100 e raised to the natural log of 2 over 9 times t. So we're just plugging in the k value. So then to answer the question, how large is the colony going to be after 41 days? Well, we just evaluate that function when t is equal to 41. So we're going to get 100 e raised to the natural log of 2 divided by 9 times 41. And perfectly fine to just leave it like that. And we've got fruit flies. So that's multiplication there. All right, so then we want to know how fast the colony is going to be growing at this 41-day mark. All right, so how do we answer this? Well, when we see this wording, how fast, that's talking about rate of change. So this is an indication, we're talking about a rate of change, and really that means derivative. So we're really talking about a derivative here. So essentially what this is asking for is it wants us to figure out the derivative when t is equal to 41. So we want to know what is the rate of change of our colony, the size of our colony here, after 41 days. So that's what P prime is measuring. It's telling us how fast our population is growing. All right, so let's first, before we go to evaluate, we'll save this for later, and let's first actually calculate what the derivative is. So let's actually calculate P prime of t. All right. And if we go back up, this is our function, and we want to differentiate it. So this is our population function. And this is what we want to differentiate. So the 100 here is a constant multiple. And actually, let's write it down here. So our population is 100e raised to the natural log of 2 over 9 times t. And let's differentiate. So we're going to calculate P prime. So when we do that, the 100 is just a constant multiple, so it stays in front. We're differentiating an exponential term, so the derivative of the exponential term just stays exactly the same. So e raised to the natural log of 2 over 9 times t. But then we multiply by the derivative of the term in the exponent. So this is our general exponential rule. So our special case of chain rule that we saw for exponential functions. So when we have an exponential function where it's e raised to the k times t, the exponential part stays the same, and then we multiply by the derivative of the terms in the exponent. And if we finish differentiating this, the derivative of t is just going to be 1, and then the natural log 2 over 9 is just a constant multiple. So the derivative here ends up being 100 e raised to the natural log 2 over 9 times t times natural log 2 over 9. So there's our derivative. And so then to actually calculate what the rate of change is when t is equal to 41, all we're going to do is plug t equals 41 into our derivative function here. And so when we do that, we get 100 e raised to the natural log 2 over 9 times 41 times natural log 2 over 9. And what are going to be the units for this derivative? Well, the units for our population function here is number of fruit flies. But because we've differentiated, we're going to divide this by our unit of time. So our unit of time here is days. So this value here, what it's telling us is how many fruit flies are being added to the colony each day. All right. So we're going to pause there, and we'll look at part 4 in class. But I just wanted to get a little more practice setting up these and solving these exponential type problems. And in class, like I said, we'll look at this one, and then we might even start a little exponential decay. So we'll see you then. Bye-bye.